Hello everyone, and welcome back. In this video, we're going to go over our first application for the NES. So with that said, let's do this. Alright, so let's get started. In this video, I'm going to go over the Nerdy Nights mirror sources for week 3, which is the 6502 assembly in our first app. And not only going to go over this source page over here first, right after I'm going to go over the code, which you can download under here under the background.zip. It's going to be under background.nes. Well, that's the compiled version, ASM. And because I'm going to cover not only both of this subject, the source and the code, is going to be a long video. But if you wish to jump to whatever part you wish for, I'm going to put the timestamps below, which YouTube refers to the next chapter. That's why I put under chapters below. And you can go to the whatever part that you feel that you're most interested in. I'm just going to go quickly over the 6502 assembly because there's some parts that I feel like needs a little more clarifications. But with that said, let's just get started. Alright, so let's go over the 6502 assembly. And like I said before, this is bread and butter for how to program the NES. So we need to know this material. I'm just going to go over quickly to go over some further explanation over here. But if you don't know the material, you can always go to I made a whole series about it. And if you wish, you can go to other YouTube and put 6502 programming tutorials or Google. There's plenty of material out there to learn the material. But let's go over it quickly. So first have a bit, which is either on or off. So here's one or off 0. So either is electricity flowing to this gate or not. That's pretty much it. And when you have 8 of them, you form a byte, which is pretty much the standard of computer. Everything is made of bytes, which consists of a value of 256 from 0 to 255. And put 2 of them together, have 16 bits, which is pretty much going to be our address space. Here's the whole value. And bits are starting from right to 0. On the 6502, so there's little endian and big endian, for instance, other way around. So it does depending on the architecture, but that's right in this case. So instructions, there are one command a processor execute. Instructions are run sequentially. And like I said, this is right for the 6502. Modern computers, because of this multi-cores that we have, that's pretty much a thing of the past. But 6502 is completely right. So let's go over our code layout. So here it says there's 5 major parts, and this is the parts that need a little bit more clarification. So here you have our directives, which are commands sent to the assembler to do things like locating code in memory. So that's right. I think of directives as pretty much as instructions for the assembler. That's how I like to think, but there are assembler specific things that do assembler specific actions that in the end of the day is always going to be converted to machine code regardless. But these are assembler specifics. So some different assemblers might have directives that other doesn't have. So that's the case. We're using the NES Emulator. In the previous videos using our older, this came to my mind right now. But there's some directives that does not correlate to one to the other. You're going to go over them at some point. So right now, directive is right. It's assembler to do things. And here's the part of the more clarification. It started with a dot and are indented. So our indentation is right. I have here on the indented under C++, which is right here. Whenever you put a tab or a space over here, even if I go back over here, you put indented. So indentation, all this space over here, there's indentation happening. So here is indentation, so a little bit of space. So let me go over here. If you see under this .org, there's a space of 2 over here, so there's the 2 space and .org. If you here see they start with a dot, they don't need to start with a dot. if you go under here, under our NESASM GitHub part over here, under documents, usage, here under symbols. So there's two types of symbols supported, global and local. So here they have pretty much our scope. So local symbols are preceded by a dot and are valid only between two global symbols. And a symbol can be followed by a column. This is not necessary, which is true because if I go back over here, if I remove this dot, the org 800 still is going to work perfectly fine. So this dot only is pretty much a matter of scope. So that's the directive, and some use 4, 2 spaces. The sample directs the assembler to put the code starting memory 800. That's what org does, put the code in memory 800, which is inside the game ROMs. Then you have labels. Labels is assigned for the far left, so there's no indentation whatsoever, and has a semicolon, which is not necessary. Like I said before, this is a locality thing or scope. So labels are used to organize your code, which is that's right, and makes it easier to read, which is also right. And translations, it's pretty much we use labels as a jump to. So this is the location 800 over here, because it started. This is putting the code at 800. Oh, excuse me. So if I put my function over here under 800, it's gonna jump to this space. If there's no arg 800, it would be jump through space 0. So then you have opcodes. So opcode, which you hear here, you have our jump instructions, which is the instruction the processor will run. So here is run. So you have the store, you have reload, you have multiple types of instructions that we can use over here. And here we have our operands, which is additional information for opcode. So this is pretty much like our parameters that we send for our instruction, for our functions in modern languages. So here is load value. So there's our opcode, and this is our operand. Here's our jump. So here's our opcode, and here is our operand, which is 800 over here. And lastly, we have the comments, like every modern language has. To do a comment, just put this dot comma over here, so and followed by our comment over right over here. So that's pretty much the 6502 assembly part of it. Now the 6502 processor over here, it's pretty much our memory mapping that we covered last video. And here we have our assembly overview. Let's go quickly over it. I already covered the part that I want you to go over. So we have the accumulator, which is the A over here, which is the main register that we do most of this loading, store, comparison, and so forth. So that's pretty much the main registers you're going to use. So here, load the accumulator in a value, then start the operating this command. So then you have X and Y, which is pretty much a counter that we use for pretty much loops and whatsoever. But, can use them for whatever, actually for both X and Y. And they're pretty much the main difference is going to come when you're doing your indirect access loading and whatsoever accessing. But in essence, that's pretty much used for counters and whatsoever. But like I said, use whatever you need them to. So then you have your status registers, and that's gonna contain our flags from overflow, from 0, from signs, and there's a bunch of other ones that we use for comparison whatsoever. So this is an important register to know as well. So this is the 4 major registers that we need to know. So let's go over some quickly instruction sets over here. We have load the accumulator over here. We have load the X and load Y. So that's going to put those values over here into those registers. You have to store over here to store those values that's in those registers. So store an accumulator. So whatever's in the accumulator is going to put in the address 2000 over here. Whatever is in the X is going to put into the address and so forth. You have the transfer what's in the accumulator to X, accumulator to Y, to X to A, and Y to A. That's the start and load ones. Then you have your common math, so add with carry, so add whatever's in the accumulator, this value. Subtract with carry, subtract with carry, both of those, this value over here, what's on the accumulator. Here we have our clear carry flag. Here you set the carry flag over here. Increment what's on the accumulator, decrement what's the accumulator on this address specifically. Increment Y, so increment the Y register, increment X, the X register. Here's the same for incrementing both of those values. Here we'll have an arithmetic shift. It's pretty much a multiply by 2, and here you have a log of shift on this address. So if this is multiply, you can think of this as divide by 2. Of course, the most important bit is gonna change. And it says over here, shift by position of 1 to the left. So here is the 0 flag over here. There's a 0 flag will be set. Important. It might be important or not, depends on the situation. And I already covered this on my 6502 programming videos, all of this. Oh, there's more. There's comparison over here. Compare what's A on this address over here. Compare in X this address. Compare in Y this address. Then you have your control flows. Jump to this address. Branch equals 0. Branch not equal 0. So this is pretty much a quick overview of our 6502 assembly codes and instructions over here. All right, now let's go over the code, which is the part that's going to take the longest. So let me try to get to it faster. And to get all these files that I have over here, this background.sm, this background.bat, which is a bat file that all it does is pretty much assemble our background.sm with the NESASM assembler, which then gives the output to background in the .NES, and as well our Mario dock character, which is the Super Mario Bros. 1 sprite. So that's all we're gonna get in this sprite. You're gonna do it later, and you're gonna use it right now. All we're doing in this first app is changing the color for the screen. In this case, it's gonna be blue. So the first thing that we have to actually do is add our INES headers. And the INES was an old emulator back in the day, and use these headers just pretty much to give information of our game to the emulator. So even it is a really popular file that it's used even to the Nintendo Switch to run emulation codes. And whenever we have this .NES over here, file ending, it's pretty much, it's going to be a INES header compile. And what it does is, well, I also have the information right over here. It's a 16 bytes here in this header. All the information that the game is going to need, such as mapper, graph, the mirroring, and our program and character sizes for our games. So your source code and sprite data. And this 4 directives is given us by NESASM. Of course, you can manually add those. You don't necessarily need to use the headers over here. And if you come over here, let me go back over here. NESASM documents. Under usage, it's going to show you all the headers and what it does. For further information, just come under the NES headers 20, which is 2.0. It has all the information. And I was planning to make just a whole video about the INES before I jump into this code, but I think it's a little bit overkill, so just gonna quickly go over it. So like I say, 16 data. I don't know what this is, so let me close it. So the first 3 is NES, and the last one's a character break, so can change this. And then the changing variables is right over here. And of course, 8 to 15 is not used. Does mean all be 0 or otherwise not work. So let's come over here. And pretty much the comment gives a great explanation what it does. So the program is the program, or source code or game is giving us each block over here is 16 kilobytes. So it either gives 16, then you have your 32, then 48, 64. You can do the whole math over here. As your games grow, because your scopes grow, you want to add more stuff. So you just come over here and increase your program code over here. Next up, you have your sprite data or character data. And that's blocks of 8. So this is a little bit smaller, but you can always increase it accordingly for what we need. Then later on, I have your mapper. So like I said before, there's pretty much a firmware that's just bank switching. That's why it says no bank swapping. And if you need to change, if you want to add a mapper for a game, come back here under this NESASM header and come right over here under mapper and name. And here's the examples of the names that actually use those mappers. So the most famous one is the MCC. You have MCC1 for Bomberman and Magman. And here you have MCC3, which is the Super Mario Bros. So it's quite popular ones. And if you choose to use another one, here's the other ones that you can add over here. So for example, MCC3 is a 4. So you just come over here, change this from 0 to 4. So that'll be the case. And the mirroring over here, in case you need mirroring for a game. So if you want either vertical or horizontal. So right now it says background mirroring 1, but then you need to come over here. And here is all the mirrorings that we can have. So here we have our, if you want a horizontal, you can 0, vertical, it's 1, what it have. If you want to use the battery and horizontal, is right over here. Let's see, vertical plus trainer. I'm not going to go over trainer, but you can go over all the information over here. So for example, if I want to do this over here, vertical, battery plus trainer, I'll come over here and give it a 7. 7. Like I said, I don't necessarily need to do this header. You can pretty much add this code right over here. All we need to do is come over here and add this 4E, 45, 55, or 53 and 1A over here. Then you give this 1 byte for this over here. Let's see, since it's 1 byte each, so define word. Let's say I think you can do byte. That byte. Let's see, what can I do over here? It's on under usage. So use NESASM assembler. DB. So you can use DB. DB. Oops. Not indented. DB. And this case will be. Oops. .db 4e. And do all the rest over here. Pretty easy. Don't necessarily use the header, but it's easier this way. And so we cover the headers. Let's go back over here. Next is banking. So the NESASM arranged their things to 8 blocks of 8 kilobytes of code. So for both the code and the graphics and the card data. And if you remember right over here, this is 16th for each blocks of program code. So all we're doing is splitting this into 8 kilobytes program code over here. So there's one bank over here. So this code is 8 kilobyte ranges for this one over here. So it starts at 0 and bank 1. So now we fill this program code over here. And the next will be bank 2. That will be for our graphic data right over here. So let's see what it says. 8 banks needed. Like most things, the computer begins at 0. Tells us similar at start. Okay, so go back to the code. And this .org over here is pretty much, that's the part that tells the assembler where to start. So all this source code is going to start at C000. If you remember from our memory mapping, that's where the game source actually starts, begin running. And then you have bank 1. This is going to be stored FFFA. And here's the 3 last vectors that's going to go over here. And here's bank 2, begins at 0. And that is not the 0 for our for the 6502. That's pretty much for the haircut data size, or not size, space. If you remember, there's 2 spaces. And one of them is for the sprites, and that's going to start at 0. Go back over here for so right over here. So this is for the CPU, this is for the PPU data, and 0 is right over here. So this is why it's 000. This 256 tiles right here. Let's go back down over here. Here we have a vectors, reset code, and compile. So instead of going over there, let's go by order over here. So we get all of this. Let's start to reset. And you know what? Let's go over the vectors actually. Right over here, you have 3 vectors. And this is pretty much a location in memory that we're going to jump. So right over here. Vectors, there are 3 times that the NES processor will interrupt your code and jump to the location. So you have 3 of them. You have our no maskable interrupt and no mask. And you have here our interrupt requests over here, external interrupt requests. So all the major difference between, well, all of them are interrupts. And this pretty much is a order of priority. No maskable is pretty much non-skippable. So you couldn't be able to ignore it. But in this case, even though it's called no maskable interrupt, you can't be ignored. So it's a little bit of contradiction over here. And normally there'll be like a major error that happens. And then the program will jump to that part so you can fix it. However, in this 65, at least for the NES, you can disable that, which you're going to go over. It's somewhere over here. Disable NMI. Not for the NES, that's not the case. So it can be disabled, but this is going to happen pretty much once per frame. So once per frame is enabled over here. So come over here, this is return for interrupt. So once per frame, so there's 1 frame happen, and it's going to come right over here, and all we're doing is returning for the interrupt. So nothing much happening over here. All we need to know is pretty much it's going to happen once per frame. Then you have the reset, and that happens when you click the reset button on the NES. So that's the hardware going. And all it's going to do is come right back over here, right in the beginning. So every time you press the reset button, and all those consoles, all it's pretty much doing is going back all the way to the top and redoing all of this initializing code right over here. And lastly, over here we have the interrupt requests. Interrupt requests are queue. And it's not used in this tutorial, but interrupt requests pretty much like any other interrupt. So if you have like a hardware happening, say a sound, and something happens, it's pretty much almost like in C++, I like to think of as not a switch, as a try and catch almost. Something is going to happen, and then it's going to tell us, hey, jump to this part of the code. So here is 0, because it's often happening. You could create something over here. Let's say foo, for example. You come to foo, and you could handle it later. But you don't really need to worry about it. At least not. Yeah, I didn't worry that much about it. But that's all the vectors. So that's gonna happen pretty much once in a lifetime. The lifetime of the NES. This is once per frame. This can be like a controller, anything external hardware, something the interrupt is going to happen, and a reset when you click the reset button right over here. So let's go over the code. So the first thing we do over here, when you reset or power on, so I was going to go over here first. Oh, excuse me. So the first thing we do is disable our REQ, which you can do right over here. You can disable that. Then you disable our decimal mode, which I believe it's tossed out from the NES 6502 versions. So that is ignored. So that's disabled, so that's a good thing. And then we're going to disable the APU frame REQ as well. So how we're doing is, right now, all we're doing is disable all these interrupt requests. Then you're going to load X register with FF. Then you're going to transfer that value to the stack. So now that if there was anything in the stack, everything now is gone. So the stack's pretty much cleared out. And we increment it. So now X is 0. And transfer all those values of 0 to disable our non-maskable interrupt over here, our rendering, and our DMC request. I covered this already, but that's the audio sounds that require a lot of data that we could play. Like I said in the example before, Mortal Kombat, when Shao Kahn happens and pointing to the thing, you're seeing, you whip pathetic fool or something, and then Goro shows up and smash the Acclaim logo. That's the DMC happening right over here. Or any saying that happens. Like in Lion King, when you press starts, all this talk data, that's the DMC over here happening. Then you have our V blank wait one, so there's 2 V blanks, so from the start to finish. And now this bit over here is a N over here, so it's doing an N, but it's not changing the value for the accumulator. So doing an N on this address. And if that address is actually, so it's not changing the value of this address over here, 2002. And while the value is positive, it's just gonna skip back to V blank wait. So V blank's not ready. So when it is ready, it's gonna come over here. That's our clear memory. So then you're going to load the accumulator with 0. And how we're doing is pretty much clearing everything back to 0, all these values. I find it interesting right over here that at 300, you're just going to load the value FE instead of 0. I don't know why. Personally, I try to find out why. Because if you see it under here in this Init Code, it is not used right over here. And I went back from some codes and ran it. I didn't see that much of a difference, but I'm going to leave it over here. I'll probably find this why. And then after all of this is done, increment X by 1. So it's going to go through all of the RAM space that we have over here and set it to 0. And then 300 round and range is going to be FE. So after all of that is done, so we clear all the RAM, so everything is zeroed out. It's going to hit on a VBlank and wait till VBlank is ready. And all we're doing over here is loading our Intensify Blue over here. So it's going to be 3 ranges, and I'm going to show you guys an emulator. And store that in our register that is going to actually affect our PPU Mask right over here. Is actually going to affect this. And then after you're done, you're just going to jump forever. And then you're going to go under whenever once per frame this happens, it should return per frame. So nothing much happening over here. And the last thing over here that I have is the include binary file, ICNB. And if you need any help for binaries or directives, what they do, just come over here in the usage. Should be all the way towards the bottom too. Somewhere over here. And include binary right over here. Binary file to current location. So if you need any help of directives just come under this document side. So that's all of our code gone. Let me see if I miss anything. Reset code. Well, here it is, PPU Max. Oh, Max. So here is completing the program. So as you see over here, every bit in this nearby over here does a different, perform something different. So at 0 is a grayscale. So if I were to mask this, would be different. So here I'm putting the value. Here it is. So pound, and then it's percentage, I mean it's a byte. So give me this byte over here. So let's change this 1 over here. So we come here at 7. This is the highmost bit. Change this to blue. If I want to change to green, I change this byte to 1. I want to add this one. And here there's other operations that we can do with PPU Mask on this address 2001. 2001 right over here. So if that's how, let's just compile everything and see how it goes. So run task, compile code, everything's good. All right, now if your code already compiled, let's go under here in the terminal, run emulator to see our changes. And as you see over here, all it does is supposed to intensify the blue, but there is only a green color over here. So you might be wondering what's going on. And like the name implies, it's only intensify the blue as a PPU mask. So to actually see the changes, you're gonna need to come over here under palette color over here. You actually change the palette color to a neutral color so you can see the changes right over here. So this is a bluish color, even though I have this gray color over here. And just to show that it actually works, let me close you. Let's change this. So we have over here our intensified blue, which is the highest most bit, the 7th. So if you see on here in the 5th bit, you can change it to red. So let's do that. So let's come over here. 1 to 5th. So let's compile our code again so our changes are made. And let's run your emulator. So it's green again. Oh, you know, and to show you all this information, we can actually come under here under debugger and memory tools, Control M. You can go to the location 2001 where the PPU mask is. As you see right over here, 2001 hex. And if you do that, which is right over here, if you put the mouse right over in the location, it actually gives you the same information and display all the stuff that you need over here, from the label to registers and what the bit does in which location that it does. So some reliable information. It's one of the reasons I like NESASM so much. Well, many reasons. Pretty much those debug tools is, I like them very much. So we have that running over here. So let's go back to your PPU viewer, palette. Let's change our neutral color. Before it was a bluish color. And here it is, changed neutral color. It shows us the red color for our emulator going. And that pretty much covered all the code for this, at least for this week's week 3 first app. And to finish it off, I'm just going to show this code running under my actual console because I have a EverDrive NES. So let's see how those changes actually affect the games inside the console. All right, and to have our game run, all you're going to need is an EverDrive, which I have over here. And all you do is put or assemble binary files inside of you have my SD card, which you're going to plug it in on the top of my EverDrive, and then you shove it into NES and just power on. And let's check how it works. So here I'm power on my EverDrive, and here's all my directories that is inside my S3 storage device. And here's are the backgrounds that are compiled by different intensities. So one is red, blue, and green. So the first one is red. And as you see, it actually works. So In some emulators might not work, but here it's working fine on my NES. So over here, just a quick display again, once again. But this time we're going to go over our background blue. So the intensity is blue for this binary file. And as you see, it does work as well. And now we're going to check if the green works. And I'm just going through all the colors to check if it actually works on the console. Because in some emulators, it won't even display unless you have to do a few changes. But as you see on the actual console, the NES, it does display perfectly fine. And here I added a gray palette. So our background is going to be gray. And just like our NESASM emulator, I put an intensified blue just to display what would happen over here. And as you see on the actual console, it's actually going to give us this blue background. And that pretty much wraps up the week 3 under the Nerdy Night series. Our first app, which pretty much just changed the color intensity for the display screen. And if you guys like what I've been doing so far, please feel free to subscribe, especially if you made this far into this video, or not. I'm not telling you to do anything. But in the next video, as you see already, you're going to go over the color palettes and go over the sprites and how to load that into your screen. But if that all said, thanks for watching, guys, and I'll see you in the next one. Bye.